Okay, good evening, everyone from SQRT and EQS. So this is the first time ever to hold the joint work journal club between SNU Quantum Research Team and Entangled Qubit Society, the quantum team in KAIST. So although both teams were established about 2 years ago, this was the first time to hold a joint journal club. So actually, the former president of EQS, Mr. Ho-Jun Lee, was my good friend when I was in high school. He was a very talented student, even in high school, with proper talents in quantum mechanics and quantum computing. So I was very grateful to be his friend, and I was very honored that he had accepted our offer to hold a joint journal club. So I would very much appreciate Mr. Ho-Jun Lee, the former president of EQS, and the current EQS members to join this journal club with us. So thank you very much, everyone. Okay, so my name is Songbin Lee. I'm currently the junior undergraduate student at the Department of Physics and Astronomy in Seoul National University. And I'm also the manager of the internship and project group of SNU Quantum Research Team. So if you're interested in any of these two topics, internships and project groups work by SQRT, then you're more than free to welcome to contact me via KakaoTalk or films or whatever. So thank you very much. So today I'm going to talk about quantum supremacy with random circuit sampling for the first joint journal club between SQRT and EQS. Sorry. So to begin, I will just talk, since this is the first journal club, I will start with very basics of the quantum computers. So what is quantum computers? It's basically a computation of quantum bits. It started from the Richard Feynman's claim that nature isn't classical. It was in 1982, more than 40 years ago. So that was very long time ago. So after 40 years, quantum computers have progressed significantly. So there are several unique characteristics compared with classical bits, if you compare qubits with classical bits. So there are 3 characteristics. I'll talk about this a little bit short on. So first of it is superposition. So if you look at this blue sphere, the figure on the right, then you can see that on the North Pole there is 0 qubit, and the South Pole there's 1. For classical bits, there's only just 0 or 1 and nothing else. However, for quantum bits, it is possible to have superposition of those 2 classical bits. It's called a superposition, and is defined as alpha 0 plus beta 1. And the probability of measuring either 0 or 1 is given as the square of the amplitude, like alpha square or beta square. So if you sum up those 2 squares, then obviously the probability has to be 1, because if you sum up all the probabilities, it is always 1. So that is the one key characteristics of quantum computers. Other characteristics includes entanglements, which is by definition entangled bits, meaning that you cannot separate large bits into 2 separate small ones. So for instance, if you define qubits as follows, this is called the bare pair states. You cannot divide the bare pair space into 2 individual qubits because they're entangled. There's no such properties in classical bits. However, for quantum cases, it is totally possible. The third characteristic is given as relative phase, meaning that if you change the phase of one of the amplitudes, like for instance, if you change the phase of the beta, meaning if you give the complex parts in the beta, then even though the probability is same, meaning that the square of beta is conserved, the full characteristics of quantum bits is different. So even though the probability is same, the qubits has different computational characteristics. So you should keep that in mind. However, this is not very important in today's topic. What I'm going to talk about is a little bit different, but I'll just keep going. So how can you calculate qubits? It's very simple. As by definition, qubits are defined as bipartite systems like 0 or 1, or the superposition or entanglement of these 2 systems. It is just, you can just compute it by like computing the vectors like in the Katz or Ross. So basically the state is defined as the column vectors given as alpha 1, alpha 2, and its complex conjugate is given as Ross, like beta 1 prime and beta 2 prime. So to sum it up, you can take the inner products. By definition, inner product is like given as how much those 2 states are equivalent or similar. So you can calculate the inner product by just taking a simple matrix multiplications. So after inner product, you get a single scalar. If you have a qubit, but you have to change the qubit, you have to get some operations. Those operations are defined by quantum gates. So if you define the quantum gate U as follows, then you can change the state psi to psi prime by just adding matrix multiplications. To be precise, the matrix vector multiplications as follows. So for instance, if you multiply 0, 0 states by with some kind of these matrices, the two Hadamard gates and the control X gates, then this qubit changes as follows. So they're by definition 4 states because it's a 2-qubit system. There's 1, 0 over here and 1, 0 behind. So there are 2-qubit systems. It has 2 to the power of 2 states, meaning 4 states possible. And currently 2 of those amplitudes is 1 over square root 2, and the other one is 0. So you can just take simple matrix multiplications to compute how the qubits propagate through time. So this quantum gate has some key characteristics since it has to preserve the probability. If you sum up the probability of all possible outcomes, then it should always be 1. If it's not 1, then it means that probability is lost, which is just basically physically meaningless. So it should be 1. To preserve the preservability, these quantum gates has to be unitary, meaning that if you check the complex conjugate of the quantum gate U, then it should be identity. It is also vice versa true. So these evolutions are all unitary. But note that measurement is not unitary, meaning that it's not reversible. If you take measurement of a qubit, then you cannot reverse it, meaning that after the measurement, you cannot recover the qubits no matter what you did. So these are the basic characteristics of quantum computers. So after we speak of quantum computers, let's move on to quantum supremacy. Like, okay, so yeah, maybe that's quantum computers, but why should you use quantum computers or why should you study? Well, because it is generally believed to be have better performance compared to classical computers, because as I told you, the qubits have physical characteristics like superpositions or entanglements, meaning that it can host 2 to the power of n bits with just n qubits. So meaning that you can have exponentially many computations parallel to the evolutions compared to the classical computers, very naively speaking. Of course, that's too naive. We're going to go a little deeper. So the statement called that quantum computers can perform better than classical computers is known as quantum supremacy. So if this question is true, meaning that quantum computer is better, then it means quantum supremacy is true. There are some problems that are exponentially faster to solve with quantum computers if quantum supremacy is true. And the currently believed examples are integer factorings, searchings, quantum Fourier transformations, and random circuit sampling, which today I'm going to talk about. So the first experimental demonstration of quantum supremacy was in 2019 by the team in Google. It was done by random circuit sampling. However, there is also a statement that quantum supremacy is false, that quantum computers have no advantage over classical computers. Those statements are known as extended Church-Turing thesis, named after Alan Turing and Alan Turing's doctoral thesis advisor, Alonzo Church. So it basically states that every physical model can be efficiently simulated with classical computers. So it has a computation analog with local realism, which basically contradicts with quantum mechanics. However, local realism was falsified by CHSH experiment in 1982. So today, we are not fully sure whether quantum supremacy or extended Church-Turing thesis, which of them is correct, but most physicists, including me, believe that quantum supremacy is true. So if it is true, then what can you do? So if quantum supremacy really wins, you can perform exponentially faster computations. The current examples are Shor's algorithms, which exponentially have faster integer factorings compared to classical based algorithms. So the left criteria is the time complexity of the Shor's algorithms to factor integer n, a large n, compared to the fastest current existing classical algorithms, which scale exponentially with the size of the integers. There's also Grover's algorithm, which is a searching algorithm, also has time complexity scaling of the square root of n compared to the classical algorithm with n. So these are the quantum supremacies. Okay, so as I told you, there are many examples of quantum supremacy, but today we're going to talk about random circuit sampling. Okay, so what is random circuit sampling? Well, actually, the definition of random circuit sampling is very simple. It is designed to be easy for quantum computers, but hard for classical computers. So after Google's experiment in 2019, several research groups around the world have performed similar experiments, even as of today. So it basically means that if you can perform RCS on a large scale, it can be expected to overcome any existing classical computers, even the supercomputers one, because basically every quantum supremacy proposals has exponential scaling in the number of qubits. So it also states that it is the test between quantum supremacy and extended church theory thesis. So how can you perform RCS? Well, to perform RCS, we have to explore the Hilbert space as quickly as possible, meaning that to generate large entanglements, which would be interactable for classical computers. So for superposition, we impose random single qubit gates. So these gates inside these green boxes is a single qubit gate. It acts on a single zero, so it's a single qubit gate. However, single qubit gate generates superposition, not entanglements. To generate entanglements, we have to apply two qubit gates, which basically is gates between these blue boxes. So these blue boxes, you can see that these two matrices coincide bipartites with two qubits, so it generates entanglements. So the actual matrix examples are given as follows. The single qubit gate used by Google's experiment was given as this square root x, square root y, and square root of omega matrices, which is a 2x2 matrix. Since qubit is a two systems, 2x2 matrix applies to a single qubit. For two qubit entanglement gates, they have used this Fermi simulation, short for FSIM, gates and control Z gates. So for specific angles, the FSIM gates are given as the matrices right in the middle of the below. So you can see that it is a 4x4 matrices. So it is a two qubit entanglement gates. So they measure the output bit strings, meaning to measure the outcomes of the entire matrix evolutions from the initial zero states and measure the real probabilities. So these are the fundamentals of RCS. However, as you can see from these PowerPoints, that this figure is very naive. We have to dig a little bit deeper to have a full grasp of random circuit sampling. Okay, so then you might wonder, why should we care about random circuit sampling? Since after all, it just apply random matrices, and generally RCS generates no useful information because it just generates random bits. You cannot use it for like integer factorings or searchings or any other useful tasks, whatever. But quantum information scientists study random circuit sampling because it has solid complex theory backgrounds, meaning that it is proven to be hard for classical computers in some sense. Unlike other alternatives like integer factorings, it is never really truly proven to be hard for classical computers. It basically states that nobody has ever found algorithms to efficiently solve integer factoring for like several 5 or 6 decades. So maybe we believe that it is hard for classical computers, but for RCS, we have some kind of solid background, some solid theoretical backgrounds. So to put that in short, it basically states that when polynomial hierarchy does not collapse, meaning that if P is not equal to NP, then approximating random circuit sampling is harder than approximating sharp P problems, which is, by the way, much harder than NP problems. So this has been proven by the several journals published like recently. So to put on the elaborate topics, I will just simplify all of the steps and be frank about it. So the polynomial hierarchy is defined as this kind of infinite series of NP oracles summing over all of the partites. So sigma 0 is defined as just P, sigma 1 is an NP problem, sigma 2 is an NP over NP, meaning that if you have NP oracle that solves NP problems, then sigma 2 is a class of NP problems that can be solved when you have those oracles. So if you have those infinite oracles, then we can go over to the polynomial hierarchy. So you can see that if P is not equal to MP, then sigma 1 is larger than sigma 0 because MP is larger than P. Sigma 2 is also larger than sigma 1 because MP is still larger than P. So, but vice versa, it's not generally true. So it means that if P is not equal to MP, but then polynomial hierarchy does not collapse. And if polynomial hierarchy does not collapse, then it is proven that approximating sharp P problems contains into the third level of the polynomial hierarchy, meaning sigma 3 of the polynomial hierarchy. However, the polynomial hierarchy itself is contained by the approximate gap P class, meaning approximate random circuit sampling class. So if the polynomial hierarchy does not collapse, then it means that approximating RCS must be harder, meaning must scale more exponentially faster compared to the approximating sharp P problems. So to give us some example, I will just focus on the single amplitude, a single probability amplitude, meaning the square of the amplitude. So I told you the square of the amplitude is the probability to measure those bit strings. So this X is defined as a bit string, and if you can define the probability of exact probability by psi exact with inner product with X, and Px is an approximation of P0X. So multiplicative error sampling means that for entire bit string X, and achieving approximations within the error of 1/2 to the power of n is gap P hard, meaning that approximacy gap P hard in this case. So this is proven in 2010. If we go over multiple additive errors, means that summing over all of the bit strings rather than posing thresholds for entire bit strings, then it is a little bit easier to solve, but it's still gap P hard. That's already proven in 2019. However, to compute multiplicative errors or additive errors, we have to compute every bit string probabilities, which is basically impossible. For quantum computers to achieve every probabilities, you have to perform state homography, which is way more, which scales exponentially in the number of qubits, like 4 to the power of n. That is simply impossible. So we have to make some assumptions to go over to the RCS, and that assumption is given as the cross-entropy quantum threshold assumption, or in short, SQRTxEQS. So SQRTxEQS basically means that if we pick P0, meaning that probability to measure bit string 0, and subtracted with exact probability, and you take a random guess to guess the probability to be 1/2 to the power of n. There are in total 2 to the power of n possibilities. So if you take a naive guess, then measuring a single bit string output is 1/2 to the power of n. So so this assumption generally means that it is still very hard to compute over the naive random guess, even for the single bit string 0. So this is basically an assumption. It has never been proven. It has been, and there are actually several counterexamples that refuse SQRTxEQS, but is generally believed to be hold for random circuit sampling experiments. Okay, so maybe this will be a little hard for some of you, but just in a single sentence, this paragraph just basically means that random circuit sampling is very important and we should focus on. It is not just kind of useless experiments like generates useless tasks. Actually, it is useless for many computing tasks, but for quantum information theory perspective, it is actually very interesting problem. So Google had actually built superconducting processors in 2019. It consists of 53 qubits. So 53 qubits means that there are in total 53 blue axes here. So you can see that there's a single gap in the middle one. So it counts 9 by 6 minus 1. So this is 53. And there are 86 couplers, meaning that 86 2-qubit gates entangle the neighboring qubits. So this is a nearest neighbor interaction layouts with 86 couplers. So it basically couples the neighbor qubits in the 40 megahertz scheme, which is very fast. It's actually one of the greatest advantages of superconducting processors. So it has this kind of following errors, meaning that if you perform like several hundred operations, then one instance should have errors, meaning that like 0 to 1, it is 0, but you measured 1, or vice versa. So the gate implementation is given as follows, but keep it short. If you correctly configure all of these superconducting hardware, then you can get this 2 cubic gate sets, which are defined as an FSIM gate that I explained earlier. So we can apply 2 cubic gates to these 86 couplers, these green matrices here on the upper right figure. So how did Google perform random circuit sampling? So as I told you, random circuit sampling is the mixture of random single cubic gates and fixed 2 cubic gates. So Google have used 3 sets of gate sets, so random circuit gate sets, square root x, square root y, and square root w. So it's a non-Clifford single gates. So to avoid Guttesman-Near theorem, I'm not going to dive in deep in this theorem. It just basically means that if you use Clifford gates, then it is easy to simulate classical. So to avoid that, Google have used non-Clifford gates. Okay, and Google also used fermionic simulation 2 cubic gates to generate entanglements, defined as follows. So Google have used in specific degrees of theta equals 90 degrees and phi equals 30 degrees for the specific experiment purpose. So after all of this, they measure the probabilities of clustering outcomes and plotted it to achieve quantum random nature. So what is a quantum random nature? After all, it is a random circuit sampling. It should be related to some quantum random nature, right? So to compare with classical randoms, if you have so basically if you have n qubits, you have in total 2 to the power of n possible outcomes. So what is the probability of measuring a single, like for instance, a 0 outcome out of 2 to the power of n possible outcomes? If it is random, it should be 1 over 2 to the power of n, right? Because it is random, there's no reason to prefer a single outcome over another. So this graph basically means that all of the probability outcomes should be all fixed to 1. The 1 is a normalized probability. So if you multiply 2 to the power of n to the 1 over 2 to the power of n, it's 1. So this graph only has like a direct delta function in a x equals 1 squared. So this is a classical random circuits. Is this correct for quantum random circuits? The short answer is no, it is not correct. So this is a simulation of quantum random circuit outcomes. So if you simulate it after several instances, then we can see that it saturates to a certain statistical distribution, which is not equal to the classical random nature. So this is the nature of quantum random circuits that Google capture after their experiments. If they have generated good quantum computers with less errors, then their computer should output this Bistrom probability amplitudes, which features quantum random circuits. So these are the claims that Google say that they have captured this random nature, which is physically different from classical systems. So how does this systems came about? I'm going to explain a little bit about the distribution. So the distribution I just show you now is called the Power-Thomas distribution. In short, PD distributions. Yeah, it is defined as like Hall measure or unitary matrix space, blah blah blah. But in short, this distribution is generated if you have sufficiently random quantum states. Okay, so the derivation of Power-Thomas distribution is not difficult. Like just take over these multiplications. Then if you just have a quantum integrals and Fourier transformations, you can just get these distributions. However, there's no need to go over exact details about the derivations. You just have to know the outcomes that this Power-Thomas distributions has exponential scaling in the normalized probability. So you can see that this y-axis is a log scale. So it means that the probability of measuring those probability amplitudes exponentially decreases as the x increases. So for ideal random circuits, as I told you, must follow Power-Thomas distributions. However, of course, our quantum computers are not ideal. They have errors. and they have all sorts of errors that are still not yet feasible today. So you have to have a quantitative figure merit to show how much our distribution is close to the Potter-Thomas distribution. So those quantitative figures are given as collision probability and cross-entropy benchmarking, which I will tell you right now. So the collision probability is basically a probability of measuring outcomes from two independent circuits. It's identical. So collision means that if you're in the same place at the same time. So collision probability also states that you measure from two different circuits, but you have the same outcome. So it's a very intuitive definitions. So the collision probability is by mathematically defined as follows. It's just basically given as the square of the probability amplitudes sum over every possible output bit strings, output possibilities. So as you can see, since it is a collision between two independent circuits, then it basically represents the second moment, meaning that the square of the probability distribution amplitudes. So the second moment of the uniform classical circuits are given as 1. So as I told you, if the circuit is classical random, then the upper probability is just focused on this average 1 values, and the second moment should obviously be 1. For circuits that are fully quantum random, meaning that as anti-concentrated nature, then the second moment is given as 2 factorial, which is basically 2. However, if quantum circuits are not fully quantum random, if they have some errors, or if they have some classical properties, then the collision probability scales exponentially in the size of the qubits. So it basically diverges. So measuring collision probabilities should be one of the quantitative figures measures that tells you how much your circuit is close from being ideal. Another figure merit is given as cross-entropy benchmarking, known as XB. So XB is defined as follows. It is basically the sum over several output bit strings like PX and QX. As you can tell you, X is a bit string and PX is the approximate probability and QX is the exact probability. So compared to the definition of fidelity, which is given as follows. As you can see, the definition of XCB and the fidelity is quite similar. However, XCB has advantage that you don't have to compute the entire bit string probability. You just have to only compute the number of samples given as n sharp here in the second equations. You just only have to compute this n sharp many probabilities to compute the XCB compared to computing the entire bit string amplitudes if you want to compute the fidelity. So XCB serves as a proxy of fidelity, which basically states that how much your approximate state is close to the exact one. So if the fidelity is 1, it means that you have an ideal quantum computers that outputs the exact quantum state you should get. However, of course, our quantum computers have errors, and the fidelity is generally much smaller than 1. And so is the XCB. So that's the reason why XCB is known to be correlated with circuit fidelity. However, recently there are several claims that XCB can easily be spoofed with sampling schemes, even though the fidelity is very small. But I will not talk about this today. So I'll just give you a quick example of how to compute XCB. So for instance, if there's a 2-qubit system, you have 4 possible output systems like 0, 0, 0, 1, 1, 0, 1, 1. If it is classical random, then you should have if it's classical random, then probability of measuring quantum state 0, 0 should be 1/4, meaning 25%. If you actually perform measurements like 100 shots, then you can get XCB equals 0. So if you compute the XCB as follows, which is basically a sum product of the classical probability and your actual experiments, then it is 0. However, for quantum computers, as I told you, their probability distribution is not uniform. They're different. So one example of being different is given as this probabilities like 60%, 25%, 12%, and 3.4%, whatever. If you perform 100 measurements and if you compute the XCB, quantum XCB, then you can see that it is generally larger than 0. So meaning that if your quantum computers really outputs this outcomes according to the probability amplitudes, then its XCB should be larger than 0, unlike its classical counterparts. One main disadvantage of XCB is that we have to compute the quantum superposition probability even as in the red box, which basically we cannot do it with quantum computers. We have to perform classical simulations to get those outcomes. So I'll move on to the Google's actual experiment results. So Google had sampled 3 billion bit streams from 10 different circuit instances, and they have achieved XCB over 0.2%, which is larger than 0. They have performed statistical tests like p-test, and their p-test value shows that their p-value is smaller than 10 to the minus 20, meaning that there's no way that the real XCB is 0, and it is all of the measurements are just lost or whatever. So as you can see on the right figure, then their error bars, their 5 sigma error bars are above 0, meaning that their joint experiments have achieved XCB greater than 0, meaning that they have captured some kind of quantum random nature in their quantum computers. So they have computed the real probabilities with Schrödinger-Feynman methods. So Schrödinger-Feynman methods is nothing difficult. It's basically computing the actual wave functions psi by dividing the wave functions into 2 and combining them afterwards. So with this Schrödinger-Feynman simulations, they've achieved Potter-Thomas distributions, and they have extrapolated their region to compute the XCB. So by definition, if they've achieved quantum supremacy, then there's no way they can perform classical simulations. So there's no way they can obtain the classical probability to calculate the XCB. What they did is that they have extrapolated these patch circuit simulations over the full circuit simulations. And they have, in the region where they can compute build probabilities, then all of the XCBs coincide nicely with each other. And so they claim that in the supremacy region where we cannot compute the full circuit amplitudes given as the red circles in the left boxes, the XCB estimation is still reliable even in those regions. So we can claim that we have achieved quantum supremacy by deriving non-zero XCB fidelity from even in those huge instances where no supercomputers can compute. So Google estimated that for 53 qubits and 20 cycles, it would take 10,000 years for world's best supercomputer to compute this similar XCB probability. So this year claims were based on extrapolating the time and memory cost, the estimated time and memory cost of their classical simulation. So what they did is they have extrapolated the figure on the right part. So for 12 circuit instances, 12 circuit depths is like 1 week and 4 years and like 600 years. If you go up to 20 cycles, then you can reach like 10,000 years. So all of these estimations are based on the memory constraints of 1 terabyte. So if you have, 1 petabyte. So if you have 1 exabyte, like in the figure on the left part, then it only takes about like several days. But obviously we don't have exabytes of memory in our computers. So those are the reasons why it takes 10,000 years for Google's Schrödinger algorithms to compute the XCB for 53 qubits and 20 cycles. So is this really the best classical computers can do? Short answer is no. Like there are more than enough counterexamples as of today because Google's experiments were performed in 2019. It's about 5 years from now, and more than 2 or 3 years ago, there have been several proposals to refute these Google's claims. I will skip the details in this part because it is very technical, but basically a team in the Chinese team sciences had computed the exact configurations of Google circuits in 3D tensors, and they achieved 0.37% XCB, which is higher than Google. another team in the United States, Simons Foundation's Flatten Institute, they have actually computed the they have achieved effective error per gate lower than Google. So Google's errors are given as 1.4% per 2 cubic gates. However, their one-dimensional tensor simulation gave us 0.8 simulations, 0.8% errors for 2 cubic gate systems in closed simulations. So most of these have claimed that they have overcome Google's experiments that claims quantum supremacy. So after 2019, there were several other experiments that have showed random circuit sampling. So in 2022 and 2021, the Professor John Wei Pan's group from University of Science and Technology of China have performed random circuit sampling up to 60 qubits and 24 cycles with XCB like 0.04%. And last year, Google have published an archive that they have achieved XCB 0.2% for 70 qubits and 32 cycles. So their experiments, they claim that their experiments are way out of reach for even the most powerful classical algorithms that have been refuted their 2019 experiments. This is for superconducting quantum computers. Other computer hardwares have also achieved random circuit sampling. For instance, for trapped ions continuum, which is a startup in the United States, just published an archive that they have achieved random circuit samplings for full connectivity, meaning that every qubit, meaning that you can entangle basically arbitrary 2 qubits, unlike just the nearest neighborhood one that superconducting quantum circuits can achieve. Similar for neutral atoms that in last year, no, I'm sorry, just several months ago, Lukin's group at Harvard, and also the group at Caltech, Professor Juni Chu's group at Caltech and Stanford have also achieved random circuit sampling experiments with comparable XCBs to those of Google's, say, USTC's experiments for superconducting circuits. So these are the current experimental progress on random circuit sampling problems. So I'll finish my presentations in a short. So random circuit sampling is important for studying quantum advantage because it has concrete complexity theory backgrounds. And quantum random is different from classical random, which is, in essence, why random circuit sampling is very useful and why we should investigate on it. And Google have claimed that their superconducting quantum circuits have claimed sampling advantage in 2019. However, there are still questions whether they have truly achieved quantum supremacy. So that's it for my journal club, and thank you for listening.